Thank you, Martin, and thank you for all the organizers for inviting me. It's really nice to talk here, and just for organizing the Friday Fish online, because every week this is great. Okay, so I will talk today about the deformation cohomology of a symplectic groupoid. This is work which is together with Christian Cardenas, who is now at the University Fluminense, and Ivan Struchiner at the University of São Paulo. And this is more or less the outline of what I'll do today. I'll tell you about how to build the deformation cohomology for a symplectic groupoid, how to use it in a Moser type argument for a Moser theorem, and then we can compute it for some examples. We'll look at how to compute this cohomology for proper symplectic groupoids and for the symplectic groupoids integrating linear Poisson structures. And finally, I'll give you some extra relations between this cohomology and the Poisson cohomology of the base which the symplectic groupoid integrates. As a small warning for the people who might have seen a different version of this talk some time ago, this is quite different because we changed our approach to the cohomology, so the definitions will be different, results slightly different, and I think reasonably better. Okay, so just out of the gate, to say what I mean by deformations, since sometimes deformations could be formal or smooth or something. When I deform a structure, I'm really thinking of deforming a geometric structure, for example, a Lie group, for example, this Lie group, that has as a manifold underlying it the positive reals times the reals, and varying the structure that I want to deform, in this case, the Lie group multiplication with respect to a real parameter. And variation of the structure should be smooth with respect to the parameter. Here, for example, we take this product of manifolds, and the multiplication in the first factor is just the usual multiplication in R plus. And in the second one, we twist it by something depending on epsilon. This is an example that I found in a paper of, a very simple example in a paper of Matthias and Rui that I really like to illustrate what sort of deformations I like. But deformations can be studied for a lot of different structures, and the philosophy that we use, and that is the basis for this talk, is that deformations are controlled by cohomology. In many classical examples, these cohomologies are known. For example, some of the most classical ones are associative algebras and complex manifolds. So associative algebras have deformations controlled by Hochschild cohomology. For Lie algebras, we have Chevalley-Alembert cohomology, in particular with values in the adjoint representation. For complex manifolds, I believe this is the oldest known deformation cohomology. We have the Dolbeault cohomology or Collider-Spencer cohomology. And this is part of, it's what inspired me to study some of the things about Lie groupoids, or it's where I took many of the concepts from. Perhaps the easiest cohomology that we can use as a deformation cohomology is the Rham cohomology, which is just cohomology for deformations of symplectic manifolds, among many other applications of it, of course. And for this audience, a very familiar one would be also the Poisson cohomology, which controls deformations of Poisson manifolds. But let's just, to set notation, and because I'll look at this later, look at the very simple case of deforming symplectic structures. Well, if we have a smooth family of symplectic structures on a manifold M, since they are all symplectic, each of the structures are closed forms, which means that if we take the tangent vector to this curve of forms, it will again represent a de Rham class. So we have a de Rham class associated to this family when we take the tangent vector at epsilon equals to 0. And the idea would be that if this family is actually a trivial family, if it can be taken by diffeomorphisms to just a constant family, then the deformation cohomology class should vanish smoothly for all epsilon. Well, one of the implications is true. Trivial families have vanishing cohomology class. And while the converse is not always true, it is true for compact manifolds M. This is the Moser theorem. And I'll just leave here a version of the Moser theorem because later I want to go back to it, not for symplectic manifolds, but for symplectic groupoids. So a version of the Moser theorem using the Moser trick is, if M is a compact manifold and we have two symplectic forms on M, such that the line of forms between them is all symplectic, and they represent the same class in the Rham cohomology, then there is a diffeomorphism in the connected component of the identity that pulls back omega1 to omega0. And the proof is the standard Moser trick. We just look for something better, which is a flow of diffeomorphisms pulling back the whole family omega epsilon to omega0. And we hope for more, and we solve that, which is that this flow would be the flow of some time-dependent vector field x epsilon, and we find that x epsilon as the solution of this equation, where alpha here is simply the transgression of omega1 minus omega0. I'm just showing this, which is very familiar, because then we'll do the same for groupoids. But moving on, we want to study the formations of symplectic groupoids. Symplectic groupoid, its definition is simple. It's a Lie groupoid, which is equipped with a multiplicative symplectic form. So symplectic form on G, which is additionally multiplicative. That means that if we pull back the symplectic form by the multiplication from G to the space of composable arrows, it's the same as pulling back by first projection, pulling back by second projection, and summing. This is a standard definition of multiplicative forms, but we can kind of skip it if anyone is not familiar, perhaps, because we'll use an alternative definition which is more suitable to our work, which is the following. Whenever we have a K-form, differential K-form, we can associate to it a map that simply takes K tangent vectors and contracts them with a form and gives a real number, okay? This map, because this was a differential form, will be a skew-symmetric map, and it will be a linear map with respect to the structure of the sum of the tangent bundle of G over G. Now we have a lemma from Enrique Agustin and Alejandro Cabrera that tells us that, well, the form that we started with on G was multiplicative if and only if this map is actually a groupoid morphism, where to make sense of groupoid morphism, of course, I need groupoid structures. Here, the structure on TG is simply the tangent of the structure of G. So TG is a groupoid over Tm, where the multiplication is Tm, the source is Ts, we just apply T to all the structure maps. And the reals are taken to be a Lie groupoid simply as a Lie group. It's the Lie groupoid with one object with the addition. Okay? So what we did was replace the condition about alpha being a multiplicative form by a condition on a map being a morphism. And I'll just leave here like short references in the bottom for the unlikely scenario that in the future someone is watching on YouTube and wants to pause and go look at the paper. Okay, so some very standard examples of symplectic groupoids are, and very simple ones are, for the non-degenerate Poisson case, we have that the pair groupoid of a symplectic manifold integrates the symplectic manifold. Well, technically, we could use the fundamental groupoid of the symplectic manifold, but in some cases, at least this is the one we want to use, the pair groupoid with the symplectic form plus the symmetric of the symplectic form. For the zero Poisson manifold, we can simply integrate it by the cotangent bundle of the base manifold, which is seen as a groupoid where the source and the target are both the projection of the tangent of the cotangent bundle. So it's a bundle of abelian Lie groups. Those Lie groups are just the fibers. And the symplectic form, the multiplicative symplectic form, is simply the canonical form on T star M. And a perhaps slightly more interesting case is that of linear Poisson structures. So for finite dimensional Lie algebra and the Lie group integrating it, if we take the linear Poisson manifold, which is M equals to G star, it's integrated by the cotangent bundle of the Lie group that integrates G, together with the canonical symplectic form on this cotangent bundle. But now beware that this is not anymore a Lie groupoid just with as a bundle of Lie groups. The groupoid structure that we have is that of the action groupoid. So remember that for a Lie group, we can trivialize the cotangent bundle as this product by right translations, for example. And that will give us a groupoid structure here by identifying this product with the total space or the arrows of the action groupoid for the co-adjoint action of the Lie group G on the dual of the Lie algebra G. Okay. So all linear Poisson structures are integrable by Lie groupoids of this form. And later on, we'll come back to this case to compute some cohomology. Okay, so what are deformations of symplectic groupoids? We'll start breaking them into pieces and study those pieces separately. So a deformation of a symplectic groupoid should be a deformation G epsilon omega epsilon of the symplectic groupoid G and omega, where G epsilon is a deformation of the groupoid, omega epsilon is a deformation of the form, such that at each time epsilon, they form a symplectic groupoid. We'll get into it later, but the first thing that we do is to switch our viewpoint a little bit, and we'll consider this associated map that takes the contraction of tangent vectors, so that this deformation of a symplectic groupoid can be replaced by a different deformation, a simultaneous deformation of these Lie groupoids, TG plus TG. Recall that TG was a groupoid, just with the tangent structure maps to the maps of G. So we can take its sum with TG again and get another groupoid. And we have a map that goes from that groupoid into the groupoid R. So we are simultaneously deforming this groupoid and this groupoid morphism, but not in any arbitrary way. It's a very particular type of deformation. So the deformation of TG plus TG is of the form T of a deformation plus T of the same deformation, right? And the deformation of the morphism is not by any morphisms, it's by bilinear skew-symmetric morphisms, which are even associated to a form which is closed and non-degenerate. So quite specific deformation. So now what we'll do is look separately at deformations of groupoids of this type and of morphisms of this type. Okay. I'll give you a very short intermezzo with a bunch of cohomologies that we'll use. So just to set notation, as you might know, for any Lie groupoid, we can form a simplicial manifold called its nerve, which has simplices manifolds of composable n tuples of arrows. So Gn gives us the space of n tuples of composable arrows, and the usual face maps that either forget the first or the last arrow or multiply some arrows in the middle. And out of this nerve, we can define the usual differential cohomology of a groupoid, or Lie groupoid cohomology. It's simply given by functions on the nerve, and the differential is simply the alternating sum of the pullback by the face maps. Explicitly, it's here in the formula, but it's not too important for us right now. One thing that I want to mention that will be important is that instead of using simply smooth functions, we could have used K-forms, and we would be able to define the differential in the same way, and we will get a very similar complex, although computing a different cohomology. Also, a different complex that we could perhaps ask for is that if this groupoid was additionally a vector bundle, for example, the groupoid TG, we could restrict not only to the smooth functions on that nerve, but to the linear smooth functions of that nerve. So there's many variations one can consider. Now, when we want to study deformation cohomology, we use a slightly different cohomology. It's not too important what this is right now. I just want to focus on the space of cochains. Cochains in degree K for deformation cohomology of a Lie groupoid G will be smooth maps that take K composable arrows and give us a tangent vector to G. The principle to keep in mind is that they give us kind of a tangent vector to a curve in G that represents a variation of a structure in G, but we'll get back to it. There are maps of this form that satisfy some conditions. It's not too important which ones, because very soon I'll pass from this complex to an isomorphic one with an easier description. The way the deformation complex of a Lie groupoid is used is that, and this is work from an older paper together with Ivan and Marius, that we showed that for any deformation of, yes.
There is a question in the chat. What is S?
Oh, I'm sorry. S is the source map of a groupoid G. I forgot to set the notation. Whenever I say S, it will be the source of the groupoid G. If M appears, it's probably the product of the groupoid G. I think those are the ones that appear the most.
Thanks.
No problem. Thank you for the question. So if we have any deformation of the Lie groupoid, so a family of Lie groupoids parameterized by a real parameter epsilon, or if you want to be more precise about how does a family of groupoids depend smoothly on epsilon, what one can see is that a deformation can be encoded by a submersion of groupoids from a groupoid G tilde to the manifold I, an interval seen as a groupoid that only has objects and identity arrows, it doesn't have any other arrows, such that the fiber over 0 is G. This would be a deformation of G. Maybe this is familiar if anyone has seen deformations of complex manifolds. Typically, they're defined in this way. It would be a big complex manifold with a submersion to a parameter space, etc. So whenever we have something like this, then we'll have elements in the second cohomology group of the deformation cohomology of G, which represents the variation of the structure maps. So something like dd epsilon of the multiplication at time epsilon. To see this explicitly, at least for a case which is a bit simpler to write down in a short formula, let's assume that we have a deformation such that the source map is not changing. It's a slightly simpler deformation. Then the deformation cocycle in the second cohomology group associated to such a deformation would just be, we take the curve in G, which is GH divided by H at time epsilon. So we take GH, we invert H at time epsilon by the inversion map at that time, and then we multiply these two things together. That gives us an element of G. So as epsilon varies, we get the curve in G, we take the tangent vector, and that gives us something in TG. The map that associates to a pair of composable arrows, such a tangent vector, is the deformation cocycle of this deformation. And what's important is that if you have two equivalent deformations, they give you the same cohomology class. But remember that we want to study some sort of simultaneous deformations when we look at symplectic groupoids. So we need to deform groupoids, but also morphisms. So for a Lie groupoid morphism,
question?
Of course, yes.
If the groupoid is proper, are there any non-trivial deformations?
Well, yes, that's a very good question, because if the groupoid is proper, then the cohomology vanishes. So it's infinitesimally trivial, but there may be non-trivial deformations. There are examples of those. But in a way that only happens because you can have deformations which are kind of flat at 0, so they're not detected by infinitesimal deformations somehow. Or they can be deformations which only happen somehow at infinity, and they're not noticed by cohomology.
Mm-hmm. Thank you.
However, I'll let you know that if the groupoid is additionally compact, then actually no, there are no non-trivial deformations, because then this infinitesimal rigidity does imply rigidity.
What about source compact? Is that enough?
No, it's also not enough. There's counterexamples for that, for using action groupoids where the action groupoids of a group acting on a vector space, and the group is compact, but the action groupoid can be deformed in many non-trivial deformations. It's a bit weird, but it happens. In any case, for morphisms, we do also have a deformation complex. So this appeared already in our paper with Marius and Ivan, but it was only mentioned there, and it's explored much further by Christian, Cardenas, and Ivan in their paper about deformations of morphisms. And the definition of the complex controlling deformations of a morphism is very similar to that of groupoids. It's just that now we take tuples of composable arrows in G and map them to tangent vectors to H at F of the first arrow. Okay, and it has some additional technical conditions, but again, we'll substitute this by a different description that will be much simpler soon. And the formula is very similar to the one for G. Okay, so this is where it starts including new things. This is from the paper of Christian and Ivan. So if you want to simultaneously deform F and G, and they also talk about what happens if you also want to deform H at the same time, but for us, let's leave it fixed. Then we have the following situation. First, we always have a map that takes deformation cochains of G to deformation cochains of F. That's very simple. It's just the tangent map of the map F itself, because this will be a tangent vector to G, apply dF, and we have a tangent vector to H in the right spot. So Christian and Ivan showed that simultaneous deformations of G and F are controlled by the mapping cone complex of this cochain map. So explicitly, the space of cochains of the cone is the sum of the space of cochains of the domain of the cone, of the map. So cochains in G and cochains in F with a shift in degree. But the cone is not a sum of chain complexes, because on the first factor, the differential is just the differential of complex of deformations of G. The second one, we have the differential for deformations of F, but it's twisted by the map that we are using to take the cone. I should mention that this is, it's actually analogous to several other situations all throughout mathematics. So perhaps the first one is already for associative algebras, where simultaneous deformations are also controlled by such a complex. This is work by Gerstenhaber and Schack. And then similar things happened in complex geometry for holomorphic maps. I've seen this in the thesis of Donatella Iacono, I think. And I think Yael Frehir also has something for Lie algebras like this. So it's very common. It's kind of a universal construction. Now, for symplectic Lie groupoids, we can, let's go back to what we wanted to do. We had simultaneous deformations of a certain groupoid and a morphism of a particular type. But since our Lie groupoids are now symplectic, we can have a better description for the deformation complex of the groupoid and of morphisms. So if our groupoid G is a symplectic groupoid, we have a chain of identifications and quasi-isomorphisms like this. The deformation groupoids, the deformation complex of a groupoid is always isomorphic to the VB groupoids of the cotangent of the groupoid. Sorry, to the VB groupoid complex of T star G. This is already in the paper of Alfonso Gracia and Meta about VB groupoids. And the idea is more or less that since this will give us a tangent vector, we can kind of pair it with co-vectors to get some numbers. VB cochains are just a subcomplex of linear functions on these groupoids, of the complex of linear functions on these groupoids. But since we have a symplectic groupoid, we know that the form omega gives us an isomorphism between T star G and TG. So actually, we have an isomorphism with the VB groupoid of TG. And the VB groupoid of TG, again, this is a subcomplex of the complex of linear functions on TG. And as a subcomplex, it's actually quasi-isomorphic to just linear functions on TG. This is in the paper of Alejandro and Tiago about Van Nest isomorphism. And this already gives us that deformation cochains on G, quasi-isomorphic to linear cochains on TG. Now, linear cochains on TG are smooth functions in degree K, are smooth functions on the kth part of the nerve of G. And what's nice is that the tangent, the nerve of the tangent of G is the tangent of the nerve of G. So smooth functions on the kth part of the nerve of G are just one forms on the nerve of G. Okay? So summarizing, our deformation cohomology for Lie groupoids, if the groupoid is a symplectic groupoid, is quasi-isomorphic to just one forms on the nerve of G, which is a way easier to understand object, I believe. Okay, what about our morphisms? So the morphism that we have is associated to a multiplicative two form. And in their paper, Ivan and Christian show that there is a deformation complex for multiplicative two forms. So what you do is you take the deformation complex for the morphism associated to that multiplicative two form, and you take the subcomplex for those cochains which are bilinear and skew-symmetric, so that we are deforming by things that correspond to multiplicative two forms, via that lemma from Enrique and Alejandro. Okay, so that's a description, but then they also showed that this complex is additionally isomorphic to the complex of two forms on the nerve of G, which is nice because now for the groupoid we had one forms in the nerve of G. For multiplicative two forms, we have two forms on the nerve of G. And since omega is a closed multiplicative two form, and we want to deform it, in the case of symplectic groupoids, we want to deform it via closed forms, it's reasonable to consider inside of this complex, the complex corresponding only to closed two forms on the nerve of G. Okay, and we denote that complex as simply the deformation complex of the symplectic multiplicative two form. Okay, now finally, we need something to put the two things together. And this is done via the tangent lift of deformation cochains. This is something that I've seen in the paper of Pierpaolo Lapastina and Luca Vitaliano about deformations of VB groupoids. And it works like this. It's a map that lets us, out of a deformation cochain for a groupoid, induce a deformation cochain for its tangent groupoid. The way it's defined, there's some technicalities, but it's not too complicated. We just compose, we take C, it's a function that goes from G to TG. We take its tangent, so DC will be from TG to TTG, and then we compose that with the flip of this bundle. Okay, this is a canonical involution. What's important is that that will be an inclusion of cochain complexes. And we can extend it very naturally to something that goes not only to the deformation complex of TG, but to the deformation complex of TG plus TG, which is what we wanted in the beginning, right? So now we have a map that includes the deformation complex of G into the deformation complex of TG plus TG. And the image will be exactly the cocycles that correspond to deformations of the form that we want. T of a deformation of epsilon, of G, plus T of the same deformation of G. Okay, I know that this was a bit of, perhaps, a lot of technicalities thrown together, but now we can put everything together for symplectic groupoids, which was the goal. So recall, we have simultaneous deformations when we have a deformation of a symplectic groupoid of Tg plus Tg, which are of this form, and of the morphism omega hat via bilinear skew-symmetric closed non-degenerate morphisms. So we can apply that mapping cone construction for simultaneous deformations. Now, any morphism of the groupoids will do this. It will induce a map from the deformation complex of the domain to the deformation complex of the morphism. If we now compose this with the tangent lift, we actually get a map from the deformation complex of G to the deformation complex of omega. And if we take the mapping cone complex of this map, that will be the definition of our deformation complex for the symplectic groupoid. Okay? Brief a little bit. So it includes, as a sum, as vector spaces, deformation cochains of G and deformation cochains of omega, but then the differential mixes the differentials and the map that relates the deformations of the domain with deformations of the form. Okay. Now, what I didn't use yet is that for a symplectic groupoid, we had this better description in terms of the Rham forms. So there's the Rham model for deformation cohomology. Since we have the deformation cochains for G correspond to 1 forms on the nerve, and we also had that deformation cochains for omega corresponding to 2 forms on the nerve. What was missing was now to check, and this is a computation, that the map that we take the cone of actually corresponds under the identifications that we had with the Rham map up to a sign, but that doesn't matter too much for cohomology. What this means is that we can use the deformation complex of the symplectic groupoid can be taken to be the mapping cone of the Rham differential from 1 forms on G to closed 2 forms on G. On the nerve of G. Here, we're taking this subcomplex that corresponded to deformation cochains, but remember that the subcomplex was quasi-isomorphic to the whole complex of 1 forms on the nerve of G. So for purposes of cohomology, we can either take the subcomplex with only deformation cochains or the whole complex of 1 forms of G, whichever is handier at the moment. Okay, and explicitly there's this formula for the differential. So it's, as before, the differential associated to the mapping cone of map of complexes. Okay, I guess this would be a good point for questions if there's any. If not, I'll show some applications. Okay, moving on.
So what?
Yes.
What controls the deformation is the first cohomology?
It will be the second cohomology.
The second cohomology.
So yes, so we have a. I'm not completely sure we are using the canonical indexing notation, but it will be the second cohomology. So the thing that has second cohomology for the groupoid and first cohomology for the form. Let me. I mean, I guess that's exactly what I was going to say next, but I forgot. So if we have this deformation of the symplectic groupoid, then, as I mentioned before, out of the deformation of G, we can form a deformation cocycle that lives in the second deformation of G. And just for a symplectic manifold, we can take the tangent vector to the path of symplectic structures, and it will live in this space again. Now, the proposition is that, of course, we had to check that this is a cocycle. And to check that, it will be basically taking the associativity condition at each time epsilon and the multiplicativity condition at each time epsilon, and taking the derivatives at time derivatives with respect to epsilon for those conditions, and then take epsilon to be 0 and check that that corresponds to the cocycle conditions. And moreover, if you have 2 equivalent deformations of a symplectic groupoid, they will induce the same cohomology class. Now, I did not tell you what equivalent deformations are, but we will see it in the next slide, just how to use this cohomology in a Moser trick. And the idea is that the cohomology was set up such that the Moser trick works pretty much almost the same as before. So now if we have a compact symplectic groupoid, or rather just a compactly groupoid and two multiplicative symplectic forms on that groupoid, such that the line of forms between them is symplectic at all epsilon, and they represent the same class in the deformation cohomology, no longer just the Rham, then there is a family of Lie groupoid automorphisms from G to G that starts at the identity. And if this was just the usual Moser trick, then we would want something like this that would pull back the form at time epsilon to the form at time 0. But we are asking more than just diffeomorphisms. We are asking that these diffeomorphisms preserve the Lie groupoid structure. So we may not be able to get just that, but we do also get a correction term. So we get a family of closed two forms, beta epsilon, which are closed forms on M, on the base, starting at 0, such that it's not that the family is completely trivial as symplectic groupoids, but the change, the only correction from it being completely trivial is this gauge transformation by a form that is in the base being pulled by the source map and being pulled by the target map and taking the difference. So this is a form when we take the pullback by S minus the pullback by T is something that is 0 in cohomology in this cohomology.
So maybe let me ask again. So this second deformation cohomology is the second cohomology of the stack of that groupoid?
There's a little, you mean if I forgot about omega, if I just said the second cohomology of G?
Yeah.
I think, okay, I'm not completely sure about this, but I had a conversation about this before with Joost Nelton, and I think there's something about this in his thesis that it's not completely the same because there's something about, how is it? There should be something about the presentation itself. So there's the formations of the stack, the formations of the groupoids, but then there could be also the formations of the groupoids that do not change the stack if they are by Morita equivalent things.
Okay.
So there is a relation, but it should be like a short exact sequence, I believe.
Thank you very much.
No problem. Okay, so this would be a Moser theorem for compact symplectic groupoids. Of course, there's other versions, so you could ask to have just paths of symplectic forms instead of these linear versions. That would be like the second version of the Moser theorem. And I think I didn't check all the details for this, but I think there's also a relative Moser theorem like this with relative to a compact subgroupoid, as long as the compact subgroupoid has a nice tubular neighborhood. So if I'm not mistaken, something like this was used by Marius, Rui, and David in PMCT1 to show that there's a normal form neighborhood around symplectic leaves of Poisson manifolds of compact type. But I think there should be the same sort of thing around other subgroupoids as long as they have a nice tubular neighborhood. And the idea of the proof is basically the same as the standard one with care. So the fact that the two forms represent the same class in cohomology means that there's a 1 form on G and now also a 2 form on M, such that their difference is the Rham differential of alpha plus simplicial differential of beta. Moreover, alpha, because d of alpha plus beta is supposed to be precisely omega 0 minus omega 1, then the simplicial differential of alpha should be 0, meaning that alpha is multiplicative. and the Rham differential of beta should be 0, meaning it's closed. And then we do the usual thing. We just take phi epsilon to be the flow of the vector field x epsilon, which is determined by the usual Moser equation. But now notice that each omega epsilon was multiplicative because omega 1 and omega 0 were, and alpha is also multiplicative. It's part of the conditions. So that will make x epsilon be multiplicative, which makes phi epsilon be Lie groupoid automorphism. And then beta epsilon can be defined just to be the correction that needs to be there to make things work. So we just take it to be t times the pullback of the original beta by the flow of phi epsilon. So for example, if we knew a priori, and I think maybe I'm mistaken, but I think this is more or less what's in PMCT. If we knew a priori that beta could be taken to be 0, then we would just have a usual Moser argument. So this would be 0. Okay. So now I would like to show you just some cases in which we can compute at least more or less the cohomology. And the first thing is just from the definition of the deformation cohomology as a mapping cone complex, there's always, for mapping cones, a short exact sequence of complexes between the two spaces that we're taking as domain and codomain of the map that we take the cone of, and the cone in the middle. And that will induce a long exact sequence in cohomology that goes like this. We have deformation cochains for omega, go to deformation cochains for the symplectic groupoid, deformation cochains of the groupoid, go to deformation cochains of omega, precisely by the connecting map that is the thing that you take the cone of. Okay, so this is just homological algebra. But then if we apply it to our case, we can, for example, compute things for proper groupoids. And recall that the groupoid is proper if for any compact in M, the space of arrows taking a compact to another compact is also a compact space subset of arrows. For example, that's the case for compact groupoids, or for paired groupoids, or for the cotangent bundle of a compact group. Okay. For these things, we will be able to use that long exact sequence, because we know that for proper Lie groupoids, this is already in the paper about the deformations of Lie groupoids, the cohomology vanishes in all degrees greater or equal than 2, and we can describe it in degree 1 and in degree 0 as some spaces. Well, the invariant sections of the normal bundle to the leaves of the groupoid, and the invariant sections of the isotropy bundle of the groupoid. So if we just input this information into our long exact sequence, we'll have a bunch of zeros that give us isomorphisms. So we will have isomorphisms between the deformation complex of the symplectic groupoid and the deformation complex of just the form for all k greater or equal than 2. Sorry, I think I meant for all k greater or equal than 3, and it should be in there. There's a shift. Let me just go back. Yeah, there's here a shift. K minus 1 to k. So, for example, H3 deformation of the symplectic groupoid is isomorphic to H2 deformation of the form, and so on. And we have a long exact sequence relating the lower terms, just by introducing what each thing is, and then we can compute a bit more explicitly some of the lower terms. But what I want to take away from this this relatively short exact sequence is just the last part, because the formations of the symplectic groupoid are encoded in this bit. And so we see that H2 deformation of the symplectic groupoid appears as the deformation in degree 1 of omega, quotient by this map, which was just the Rham differential in our Rham model, applied to H1 deformation of G. which we also know corresponds just to invariant sections of the normal bundle. So it's a more or less explicit description. Okay. Now, a different way in which we can compute the cohomology is the following. Since it's a mapping cone, it can be realized, the complex, which is a mapping cone, can always be realized as the total complex of a double complex. We just take one complex to be the domain, the other complex to be the codomain. We put between it the complex morphism that we're taking the cone of, and we get a very simple double complex. It only has 2 lines, right? And see that indeed, if we take the anti-diagonals, we'll have the things that we take the sum of to form the complex, the cone complex, and indeed, in one direction, we just have the differential of one of the complexes, while for the other, we have the differential twisted by the map D. And here we already see that this shows up as a certain subcomplex of the Bot-Schulman-Stashev double complex, which would be, if we don't stop here at degree 2, but we take not only closed forms, but all forms in degree 2, and then K forms in all degrees. So this was an earlier version that we had of the deformation cohomology for symplectic groupoids, was just to take Bot-Schulman-Stashev total cohomology. And I remember at the time it seemed to be a bit too big. It included too many things that didn't seem to relate directly to deformations of symplectic groupoids. So now we identified the bit inside of it that does control the deformations of symplectic groupoids. One of the reasons why I like to describe it like this is that now we can use spectral sequences to compute it, and very simple spectral sequences, right? Because if we want to do the spectral sequence of a double complex, it's a simple one. And when it only has 2 lines, it's a very simple one. So we could, for example, just first take horizontal cohomology, simplicial cohomology, right? And then take the Rham cohomology induced on that. And then the next differential is already always 0, so we wouldn't have to compute anything else. Or we could take first the Rham cohomology, and then simplicial cohomology, and then we may have to still compute something that goes a bit to the side and down, but in some cases we don't. And I'll show you one now, and this will be more or less towards the end of the talk. So let's do that. I want to do the columns first spectral sequence. So if we just take the columns first spectral sequence, we will be computing the Rham cohomology, right? So here we take the kernel of this, which is, well, everything, so closed forms, modulo, exact forms, so we'll get the Rham cohomology in degree 2 of the nerve. While in the 0th line, we take, well, just the kernel, because we didn't have a -1 line, so we just closed forms on the nerve. So now we would have to take horizontal cohomology induced in these by the simplicial differentials. And I'm not claiming that this can be easy to compute in all cases, but there's a case in which it is, which is for linear Poisson manifolds. So for a linear Poisson manifold, if G is the one connected Lie group integrating the Lie algebra G, then we can show that there are isomorphisms between the deformation cohomology of the symplectic groupoid T star G and the Poisson cohomology of the base. In degrees 1 and 2, there's almost an isomorphism in degree 0 up to constant. And in degree 3, we have an injective map from deformations of the symplectic groupoids to the deformation complex of the Poisson manifold in the base. And these are the degrees that are important for deformation theory, right? Because in degree 2 is where we have infinitesimal deformations. In degree 1, we have infinitesimal automorphisms. And degree 3, we have infinitesimal obstructions to realizing infinitesimal deformations as actual deformations. So what this theorem says is that essentially at the infinitesimal level, the deformation theory for this symplectic groupoid and this Poisson manifold is the same. Because if we have something that is unobstructed, how is it? So this map is injective, meaning that obstructed things cannot go to unobstructed things. Okay, so let me give you an idea of the proof. First of all, just to recall, I'll be very brief in this, but this cohomology, the Poisson cohomology, in case anyone is not familiar, is the deformation cohomology for Poisson manifolds, and cochains are simply multi-vector fields, and the differential is the Schouten-Eyenhaus bracket with the Poisson bivector. Okay. Now, how do we compute it? The deformation cohomology for these symplectic groupoids? Well, it's simple. We'll do the columns first spectral sequence. And what we obtain is this. This is just for any symplectic groupoid. But now, the trivialization that we had for T star G as an action groupoid lets us see that the nerve of these, or the nerve of the action groupoid, is just n copies of the group G times the dual of the Lie algebra. And we are, this pi should be pi 1, so we're taking the simply connected integration of the Lie algebra. Pi 1 is 0, and pi 2 is 0 for any Lie group by a result of off, right? So this means that since this is contractible, and these are just copies of the same Lie group, the nerve has 0 as first and second, the Rham cohomology equal to 0 for any space of the nerve, right? So this line will just disappear, and this one will become simpler. Just 0, and closed forms are just exact forms, okay? So immediately this becomes way simpler, and now we just need to compute this horizontal cohomology. You see that this is almost the same as having just differentiable cohomology of the groupoid G acting on G star, except we're taking D, so there's a correction by constants. So formally what this means is that the Rham differential will be surjective from functions on the nerve to closed forms on the nerve. And since the nerve is a bunch of connected manifolds, the kernel consists of the constant functions in each degree. And if you go look at what the differentials are in this subcomplex, there are 0, identity, 0, etc. So the cohomology of this will be R and then 0, 0, 0, 0, 0. So when you take the quotient, you just get that you get differentiable cohomology of the symplectic groupoid that we started with, modulo R in the first case, and just simply this in all the other cases. So the theorem actually says a little bit more. We can compute the symplectic groupoid deformation cohomology to actually be this. But then, by the Van Est map, since the fibers are too connected, we can relate that with the Poisson cohomology, because Poisson cohomology is the same as the algebroid cohomology of the algebroid corresponding to this groupoid, right? So that gets us to the conclusion. Okay, I think I still have 2 or 3 minutes, so I'll just let you know that there's a few other examples in which we can do basically the same trick. So what did we use? We just used some things about the topology of the symplectic groupoid. So if we had a symplectic groupoid for which the source fibers are 2 connected, and such that the base is 3 connected, and such that the source is a vibration, this might seem like a lot, but it happens sometimes, then we have the same conclusions. The cohomology of the symplectic groupoid is up to constants in small degrees, the same as the deformation the deformation cohomology of the Poisson manifold, which is the base. Okay, the proof would be just go back and repeat everything. The conditions are just to guarantee that the nerve of G has vanishing first and second the Rham cohomology. So that would be really the condition. These are just technical conditions that ensure that that always happens. Using some long exact sequences in homotopy. So this will happen, for example, if you just take the symplectic groupoid integrating the 0 Poisson manifold for a 3 connected Poisson manifold N. And it also happens, for example, for some duals of Lie algebroids and their corresponding symplectic groupoids, integrating them, as long as you take some care of the topology of those Poisson manifolds. So it happens in some cases. And my time is almost over, I think. So here we see that when the topology is simple, the deformation cohomology of the symplectic groupoid is very related. It's almost the same as the deformation cohomology of the base manifold. But in general, when the cohomology, when the topology is not simple, there's still a relation. And the relation is more or less the following. For any Poisson manifold, there's an associated Lie algebroid. So deforming the Poisson manifold by other Poisson manifolds induces a deformation of Lie algebroids. And there is a deformation cohomology for Lie algebroids, which was defined by Marius and Ike. And essentially, it's given by, well, multi-derivations on the algebroids, which is a complex which is isomorphic to the complex of linear multi-vector fields on the manifold A star, where a multi-vector field is linear if when you contract it with linear vector fields, it gives you a linear function. So what Marius and Ike proved is that, well, there's always a chain map that goes from the deformation cohomology of the Poisson manifold to the deformation cohomology of the Lie algebroid associated to it, which simply sends a multi-vector field to a multi-derivation, which is defined by, well, a certain formula. That's not perhaps too important right now. And they prove that it sends the deformation class of a Poisson manifold being deformed to the corresponding deformation class of the deformation that corresponds to it. Now, I'll just tell you that for groupoids, we basically managed to define a similar map. And what we do is that since our deformation cohomology for a groupoid was quasi-isomorphic to linear cohomology for T star of G, we'll use this complex instead. And we want for a groupoid cochain to induce a deformation cochain. And the way we do it is just by, out of a deformation cochain, taking a tangent lift to get a cochain on TG, and then using the symplectic form to identify these two and get a linear cochain on T star G. So we get a map that goes precisely from groupoid cohomology to deformation cohomology. And the theorem is that when you take cohomology, this map corresponds to the map of Ike and Marius via the Van Est maps. And I will perhaps skip the ideas of the proof, but just let you know that it involves a lot of identifications, and very carefully, this was done by Christian, who did a lot of careful checking between the compatibilities between all the Van Est maps, the tangent lifts, the morphisms, omega sharp and their corresponding Lie algebroid morphisms, checking that everything fits together. And finally, if we look at everything turned into the Rham model, this map that we described becomes simply the Rham differential. So we kind of finish a little bit more of the Bott-Schulman/F double complex. We have really something like a good truncation, so we cut it at level 2, but take only closed things at the line 2. It's a bit tricky because it's a double complex. And so that this part here is what describes the formations of symplectic groupoids. This part here is the part that describes the formations of Lie groupoids. And this is the map that induces the formations of Lie groupoids out of Lie groupoid cochains. Okay, now I'll stop here. Thank you.